Thank you everyone for coming to this webinar. Amazon Quantum Ledger Database, a source of truth for your data. We are presenting this in association with the Columbus AWS Meetup, but you certainly don't have to be a member of the Meetup to attend. Now, your presenters today are myself, Andrew May. I'm the Cloud Solutions Lead at Leading Edge. I've been with Leading Edge for, I think it's 13 plus years now, working on a variety of cloud projects over the last 5 or 6 years. Dan, if you want to introduce yourself.
Sure. Hey, guys. So my name is Dan Blainer. I'm a solutions architect specializing in quantum ledger database. I work for AWS. And so I spend my days helping customers understand what a ledger database is and helping them build applications to use QLDB, to use ledger technology.
Thanks, Dan. So Leading Edge is an AWS partner network select consulting partner, and we're based in Columbus, Ohio, but we have clients and edges, as we call them, all around the country. Some of them even from overseas. We specialize in cloud native development, and we're doing a lot of migrations to the cloud as well, and DevOps work. And we're always looking for qualified cloud developers, engineers, and architects. And if you're interested in seeing what openings we have, hit us up on the website. Now, as I mentioned, we're doing this in association with the Columbus AWS Meetup. I'm sort of one of the frequent attendees and presenters at the meetup. And things have been a little quiet over the last year, but we're hoping to get more sessions in this year. So feel free to suggest a topic or volunteer to present. Hopefully in the near future, we'll be able to have meetings in person again, although I suspect we might do some hybrid meetings to start with. There will be a survey at the end of the session, and a couple of the questions in there are just about topics you might be interested in learning more about. Okay, and with all that said, I'm going to hand over to Dan, who's going to give an overview of QLDB.
All right, thanks, Andrew. So I'm going to go through a few slides. As I go through the slides, feel free to ask questions. We have moderators that can take questions. On the line with me is Alan Newcomer, a fellow specialist SA, as well as Eric Kramer. He's a product manager for QLDB. So we're happy to take questions during my presentation, but also we'll be around for Q&A after. So with that, let me make sure I click the right screens here. All right, Andrew, am I sharing?
It looks like it.
All right, very good. Okay, so on the screen here is an old ledger book. If you've ever done the books for a small shop, maybe you've seen one of these before, but this is a ledger. So humans have kept ledgers for thousands of years to record financial transactions, to keep balances, and to register significant events, things like births, transfers of land ownership, emigrations, etc. What's interesting about a ledger is that a ledger keeps track of all transactions over time. At any point, you can flip back in the pages of that book and you can see every transaction ever recorded in the book. If you need to correct information, you don't sort of cross out information in the ledger, you add a correcting entry. And so the ledger represents a complete history of everything you've ever recorded in that book. So at some point in human history, we decided to start using computers. However, storage was very expensive in early computing when databases were invented. And so databases were designed for storage efficiency, and they were designed to overwrite data in place. And it's now that we have very cheap storage and we have cloud that gives us almost limitless storage for a very low price. It's only now that we have the ability to create databases that keep a complete history of every transaction ever recorded in that database. And that is what a ledger database is. A ledger database gives you a complete history of every transaction. So what is QLDB? If I can flip my slides here, here we go. So QLDB is a fully managed ledger database that maintains a complete and verifiable history of changes over time. And those two words colored in orange there are the two reasons that QLDB exists: complete and verifiable. when we say complete, we like to use the word immutable. So whenever you record a transaction in QLDB, that transaction is written to the journal, and it can never be modified, overwritten, or deleted. So QLDB gives you a complete history of everything you've ever committed to the database. And when we say verifiable, we use a cryptographic hash chaining technique that allows you to mathematically prove the integrity of your data. It allows you to prove that your data has never actually been changed or tampered with. And these two qualities are the reasons QLDB exists. And they're fantastic for applications or for companies that might be facing scrutiny from auditors or regulators, or might be involved in a legal action where they have to prove the integrity of their transactions or provide transparency into what they're doing. Or it's great for any case where you need to sort of prove the integrity of your transactions or transaction history to another party. It could even be the public or business partner. And so QLDB is one of the only databases available that give you these two qualities, that give you an immutable and verifiable transaction history. And so let's see how that works. So QLDB is built on something called a journal, and the journal is very similar to a database transaction log. It's an ordered sequence of blocks. All writes go to the journal. It's where we determine state. It's also where we handle concurrency and sequencing, our cryptographic verification function, and availability. So it is an ordered sequence of transactions, and those transactions, again, are permanent. Now, that data structure is difficult for an application to access. Imagine always having to reconstitute current state from that big, long history of changes. And so what we do is we materialize data from the journal into several views, into a document style, non-relational database interface. And that's how you primarily interact with the database. And so we provide several different views in that database for you to use. The top right there is the user view. So this gives you the current committed state of your data organized in tables. And so if you always want to see just the current state of your data, then you can use the user view. The committed view there in the middle is the same as the user view, but we surface metadata that QLDB creates on your behalf. So you have access to internal identifiers, transaction information, and the cryptographic hashes for your data. And then finally, we have the history function, or the history view, and that gives you access to every revision of that document over time. And so when we say immutable, some people think that it means that, I write data to the database and I can never touch that record again. What you're really doing is you're creating revisions of a document. And so those revisions exist in the journal for all time. And with the history function, you can see a complete change history, a history of every revision of every document. And so the combination of these three views gives you a choice in how you want to access your data. Do you want to see just the current committed state of your data, or do you want to see the historical revision history of your documents? And so this gives you a very flexible way of accessing your data. So the transaction history in QLDB is immutable and complete. Once data is committed to the journal, it can never be touched again. It can never be altered or modified or deleted. So the journal is a complete record of all committed transactions and revisions. There are no APIs for you to be able to modify the journal, modify committed data. Once you commit data, it's there forever. There's no administrative function for you to use to modify committed data. There's no function that you can do. Once it's in there for good. And so the journal looks a lot like this diagram. Every time you commit a transaction, we group your data into a block. We append that block to the end of the journal. And so the journal looks like a sequence of blocks that each represent a transaction. Cryptographic verification is a process that we use to mathematically prove the integrity of that journal. Essentially, a cryptographic hash is a fingerprint of your data. You can take any amount of data, run it through a cryptographic hashing algorithm, and it produces a fixed width hash. And that's essentially a fingerprint of your data. If you change even a single bit in your input data and run it back to the algorithm, it produces a very different hash. And so by comparing hashes of data at two different points in time, you can easily tell if that data was changed because the hashes will come out differently. And so the cryptographic hash chaining is a technique that we use to do our verifications. So here on the left, we have two documents that represent records in QLDB. They are identical in every way except for the last digit of the curve weight field, colored there in orange. you can see that they vary by 1 digit in that one field. And so if you look on the right side, you can see that that their cryptographic hashes come out very differently. And so by simply comparing those two hashes, we know that they were created with different data. And so this is at a very high level, the fundamental mechanism for us to do verification. When you commit data to the database, QLDB calculates and stores a hash. And then later on, when you want to verify that data, you recalculate the hash and compare it to what you had before. And the SHA-256 hashing algorithm is essentially one way. If you start with a hash, it is computationally infeasible for you to reverse engineer that hash into the input data. And so it's a very secure algorithm to use for verification. Now, as I mentioned, QLDB is a document style non-relational database. We do support ACID compliant transactions, and we do that at the serializable isolation level. The serializable isolation level gives you the highest concurrency protection. So you don't get phantom reads or non-repeatable reads, dirty reads, or write skew. This isolation level is available in relational databases, but it often comes with a significant performance penalty. And so relational databases will often default to a read committed isolation level that gives you a balance between concurrency protection and performance. However, in QLDB, we can offer the serializable isolation level to give you the maximum concurrency protection without any degradation in performance. And so, again, QLDB supports ACID compliant transactions at the highest isolation level. QLDB is easy to use. It is a schemaless document style non-relational database. And so the data that you store in QLDB is in the form of Amazon Ion documents. And Ion is a superset of JSON. So if you're familiar with JSON, you'll be pretty familiar with Ion. We essentially took JSON, we added a few native data types to it, and we released it as an open source spec called Ion. So when you are interacting with QLDB, you are interacting with Amazon Ion documents. And you query your data using Particle, which is a SQL-like query language that natively understands complex structured documents. So with Particle, you can query data in a relational database, data in a document database, or even in a Parquet file sitting in your S3 data lake. It's a very flexible SQL-like language that natively understands schemaless databases and structured documents. QLDB is a regional service for AWS. It operates at the region level, and we automatically replicate your ledger across multiple availability zones in an AWS region and in multiple physical locations in each of those availability zones. So whenever you commit a transaction in QLDB, when you get the successful response back from the service, we've already written your data to at least 2 AZs and are working on the rest. So this gives you very high availability and very high data durability. We also handle scaling on your behalf. So you don't need to pre-provision storage. You don't need to pre-provision compute or IO. You simply create a ledger using the console or the SDK or the CLI and begin throwing traffic at us, and we'll handle scaling for you. So here's a quick example of how data flows through QLDB to give you an example of what we mean by the immutable ledger. Pardon me. So on the bottom there is the journal. You can see that it's currently empty. On the top right there, we have the cars table that represents the current committed state of your data, what we call the user view. And right below it, we have the history view. So we're modeling cars in this example. So we'll insert our first vehicle. And you see we run an insert statement up top. That creates a new transaction, which creates a new block. And that block is appended to the journal. And then what we do is we propagate that data into the cars table and into the history view. Now we want to change the owner of that vehicle. So we run an update statement. So that statement creates a new transaction, which creates a new block. We append that block to the journal and we hash chain it to the block before it. Now the cars table, which represents the current committed view, now reflects the new owner because that is the current committed state of that record. However, in the history view there, you see that we have both revisions of that document. Now, finally, let's say we want to get rid of that vehicle. Maybe it was totaled. So we run a delete statement. That creates a new transaction, which creates a new block, and that block is appended to the journal. And then what we do is we propagate that data into the cars table and into the history view. Now, we want to change the owner of that vehicle. So we run an update statement. That creates a new transaction, which creates a new block, and that block is appended to the journal. and is hash chained to the block before it. Now you can see in the cars table, we've removed that vehicle record from the cars table because that represents the current committed state of your data. However, in the history view, you see that we have not removed any of the history, and we've in fact added what we call a tombstone record to indicate deletion of that vehicle. So you still have access to all 3 revisions of that vehicle record, the insert, the update, and the delete. And most importantly, you see the journal still maintains a complete record of the insert, the update, and the delete. And this shows you, it demonstrates the immutable nature of the journal and what we mean when we say that it represents a complete history of every transaction ever committed to the database. But it also shows you how you might use the cars table or use the user view compared to the history view for your applications. So what is QLDB good at? And by extension, what use cases would QLDB be good for? So QLDB is a great audit database. It's where you would store an immutable and verifiable record of changes to your critical business information. So you can keep track of your customer data, keep track of critical private information, and see how that information has changed over time, giving you essentially an unfalsifiable audit of things that happen in the database. And so using QLDB as the audit database is a great use for QLDB. It's also great for event-driven architectures. So in an event-driven architecture, you can use QLDB to model state changes for an application or an entity. And what QLDB gives you is a complete audit history of changes to the state of that object over time. We'll look at some architectures in a little bit that'll help demonstrate why QLDB is great in an event-driven system. But we have a lot of customers using QLDB to model events and to model event flows as those events pass through the system and onto downstream systems. So again, it gives you a complete change history, a complete unmodifiable change history of state changes to those objects. QLDB is also great for transactional system of record. So we have a lot of customers in banking and finance that use QLDB as a transactional financial ledger. And so QLDB is great at storing a consistent and authoritative record of important business information. And so you can manage changes to that data, but you can also have a complete and unfalsifiable history of changes to that information. And finally, QLDB is a fantastic blockchain alternative. Many blockchain use cases, I think, would be better served by using QLDB. It's a great alternative to blockchain. If you've ever looked into building on blockchain, blockchain is a very complicated technology. It's complicated to set up. It's complicated to operate. It involves your business partners having to operate blockchain infrastructure, and the development model for blockchain is really different than most development models that developers are used to. And so if your developers are already familiar with working with a non-relational database, especially a non-relational database in the cloud, then working with QLDB will be very natural to your developers. So you're going to build architectures that most developers should already be familiar with. Now, QLDB is optimized for high volume of write traffic, and it's optimized for very targeted fetches of data using indexes. And so QLDB is not great for analytical databases where you're churning through a large volume of data. It's not optimized for scanning through large volumes of data. You want to do very targeted index hits when fetching data from QLDB. And so QLDB is not great for analytical databases. I'll show you a design pattern in a few slides here that show you a typical architecture for using QLDB as a system of record or source of truth, and then pushing data elsewhere for doing analytical workloads on data from your ledger. So again, QLDB is it's not really built to be optimized for analytical database workloads. It's also not great for non-transactional workloads. It's optimized for transactional workloads. And if you're looking for basically a non-transactional event distribution bus, then there are other alternatives that would serve that purpose better. Certainly things like SNS or SQS or Event Bridge or even Kafka or Kinesis would be a better if you don't need a transactional element to your event architecture. So QLDB is specialized as a high volume transaction bus essentially. So if your workload is non-transactional, then maybe QLDB is not optimized for what you want to do. So let's talk a bit about some architectures for how you would build on QLDB. So QLDB offers a feature called streaming. And what streaming does is allows you to pair a Kinesis data stream with your QLDB ledger. So whenever you commit a transaction into QLDB, QLDB will push that data into Kinesis, where you can react to it. You can use that to drive event-driven logic using Lambda or containers. You can use that to drive real-time analytics. Or what many customers do is they use that as a mechanism for pushing data from QLDB into other purpose-built database engines for handling different read workloads. So it's pretty common for customers to use QLDB as their system of record, and then to push data into, say, Elasticsearch for doing text search, into Aurora for doing reporting or ad hoc query, or even into Redshift for doing your OLAP style workloads. So here's what that architecture looks like. This is a very common architecture for QLDB, and it's one that we recommend for almost every QLDB workload. It's what I call a write-through streamout architecture. So on the left there, you have your application. It's interacting with your application that's running on some form of compute. I've got EC2 listed here, but frankly, what we mostly see is API gateway backed by Lambda, or applications running on containers, ECS, EKS, Fargate. Those applications will interact with QLDB using one of our drivers. We have drivers in most popular programming language. So you interact with QLDB as your primary database, and then QLDB pushes data from QLDB into a Kinesis data stream where you consume that data from using Lambda and then push it into one or more downstream databases or systems. So this is a common integration pattern, downstream integration pattern for QLDB. And a lot of our customers will use this mechanism to push data into Aurora, into Elasticsearch, or even into their own internal backend systems. Maybe they have their own databases, or they have their own internal APIs that they need to push data into. And so this is a great mechanism for doing that. And again, it's a pattern that we see most customers using. So what this allows you to do is to use QLDB as your source of truth, and as your transactional system of record, and then allows you to direct certain read traffic into the database that is best optimized for that read traffic. So again, text search by Elasticsearch. If you want to do analytics, then Redshift is fantastic. Or if you are doing reporting or standard reporting or other operations, then Aurora is also great. So again, this is a pretty common architectural pattern. Another important pattern is what I call a data lake or batch integration. So QLDB offers an export capability that allows you to export all or part of your ledger into S3. And the export is block level files. So you're not getting just your data, you're getting information about the transaction, you're getting your cryptographic hashes. And one interesting thing is that we also store the particle query statement in the blocks that were used to create each transaction. So these exports give you a great audit capability that allow you to see every query ever run against your database that resulted in a committed transaction. So running an export and then breaking out the data from the export that you need using an ETL or extract, transform, load process into another S3 bucket or your data lake is a great way of giving access to that data from some of our serverless compute services, things like Redshift Spectrum, Amazon Athena, or even Amazon EMR. And so this is a pretty common data lake pattern, but it's also great for, if you need to do occasional reporting queries and you don't want to pay full time for compute like Aurora, then what you can do is you can run an export into S3. You can do a quick transformation to extract the data, and then you can use Amazon Athena to dig through that data. And you only pay for the compute services that you are using. You pay by the second that Athena is running the query. And so this is a great offline pattern. You can also use this process to push data into other customer systems. So if you have your own data warehouses or you have your own applications that don't need a real-time feed of data, you want to do a batch job, maybe nightly, then this is also a great pattern to use. And so these two mechanisms, Kinesis, streaming, and our export, are your primary downstream integration patterns. And the decision of which to use depends on, do you need the data in near real time? If so, then use Kinesis. If you don't want it in near real time and you want it in more of a batch style or occasional approach, then use the export mechanism. And so these are two very popular patterns for building applications on QLDB. So to wrap up, what makes QLDB special is a fully managed ledger database service. It's immutable, so it gives you an append-only, immutable history of every transaction ever committed to the database. And I don't think I mentioned this, but actually, every query in QLDB is transactional. So of course, inserts, updates, and deletes are transactional. You would expect to see those in the journal, but in QLDB, read-only queries are also transactional, and they'll create a block in the journal. And so therefore, the query statements for read-only queries are available in the exports. And so this gives you a history, not just of your inserts, updates, and deletes, but also every query, every read query that was committed against the database. So it's a fantastic way for getting an audit of your data. And so again, what QLDB gives you is an immutable transaction history, built-in data lineage, and an unfalsifiable audit history. The journal is verifiable, so you can mathematically prove the integrity of your database. You can prove to other parties that your data has not changed or been tampered with. And that gives you some transparency and openness with your partners or with those that you need to prove the integrity of your data to. QLDB is serverless and fully managed. We handle the scaling on your behalf. So there's nothing for you to pre-provision. You just simply create a ledger and begin throwing traffic at us. And it's also very easy to use, especially if you compare it to blockchain. But if you've used other non-relational databases, QLDB is really easy to use. It has a very flexible schemaless data storage format in ION, which is a JSON-like data format. And you query QLDB with a query language called Particle that looks a lot like SQL. So if you're familiar with SQL, then learning Particle, is no great leap. So that's why you would use QLDB. And again, it's great for those cases where maybe you're facing audit scrutiny or legal scrutiny or regulatory scrutiny, or you just need to prove the integrity of your transactions or provide transparency into what you're doing to other folks. And so with that, feel free to reach out to me on LinkedIn. Feel free to connect, or if you just want to follow up and you have additional questions, here's how you can reach me. So with that, Andrew, I'll apologize. I came across 6 minutes early, so I'll hand it back over to you.
Many thanks, Dan. Okay, so now I'm going to try and demonstrate some of the things that Dan has been talking about with an example. Okay, so hopefully you should be able to see my screen. Okay. I am screen sharing. That's good. Okay, so this example is really an event streaming example similar to one of those examples Dan provided in his slides. And we're making use of this immutable auditable record of data. In this case, we're receiving it via an API gateway, just as Dan suggested. So we can query the table, and we're just going to put data into a single table in this example, either for the current version or history, and we're going to show you that. And changes are going to be made available using a stream of events. And this is inspired by a client project where we've used QLDB. Now, our basic architecture here is an API gateway that feeds to a Lambda function. Everything that goes to the API gateway is mapped directly onto the Lambda function. We've just got a single Lambda here. And then we're talking to QLDB. So our data is coming in as JSON, and it gets passed on to the Lambda function still in that JSON format. When we start dealing with QLDB, we need to be working with IAN format, and there's just libraries here to convert between the two. Now we're going to do this kind of select insert pattern, update pattern that I'll describe in a second to determine how we manage data into that, whether we insert or update a document into QLDB. Additionally, we're going to be sending off a filtered copy of the JSON version of the data to SNS. And the reason we're doing that is because when we get a new document, if we do an insert, we're going to send it to SNS. If it's an update, we're not going to. So we're going to make a decision based upon what's already in the ledger. Additionally, all the changes are going to go to a QLDB stream in Kinesis, and we've got a simple stream consumer that's just logging to CloudWatch. So the data in the stream is all in IAN format, and that's what the stream Lambda is consuming. Now, primary keys and indexes. QLDB is going to assign each document you insert a unique identifier, a UUID. And while you can assign indexes yourself on single top-level fields, the uniqueness of these fields is not enforced. So you can't really have your own primary key where uniqueness is enforced by the database itself automatically. Now, if you're able to make use of the document identifier that QLD provides for you, say you do an insert, you provide back in your response that document identifier, and then that's what you use for updates, that's fine, you can certainly do that. If you want to use your own identifier, or you're using an identifier from a third party, you want to follow this pattern shown below, because otherwise, if you're not careful, it is entirely possible and probably not desirable to insert exactly the same document multiple times. So in this case, we're saying that we've got data, or API event is our table, and we've got an ID field. We're indexing that ID field, and that's our sort of identifier, our business identifier that's being sent in the event we receive from the third party. If we find a match, we're going to do an update. Otherwise, we're going to do an insert. And because everything's done within a transaction in QLDB, we can guarantee that we're not going to accidentally insert twice with the same ID value. Now, something else I want to highlight in this demo is some new functionality that was just recently added to QLDB, and it's called the standards permissions mode. This gives us much more fine-grained IAM permissions for the ledger than we had previously, and allows us to control access both at a per table level, but also a per operation level. So you can see the permissions map very closely onto the particle commands. So if I want to create a read-only user who can only query the ledger, I mean, it may be that the ledger will track every change, but that doesn't mean that we want to allow everyone to do deletes, even if we could recover the data. So this allows us now to grant read-only users, or just limit what a particular Lambda function or compute or IAM role is able to do with the ledger. Now, I'm going to show you a demo. All of the code for this is available in GitHub under my GitHub account. I've got the link here, but it'll also be shown at the end of the presentation. And we're using a mixture of CloudFormation and the serverless application model for deploying both the sort of underlying resources, the ledger and the stream, and then SAM for deploying the functions. And these functions I've written in Python. So this is going to be a live demo, so what can possibly go wrong? The steps I'm going to be going through: create the ledger using CloudFormation. We're going to manually create the table and the index in the console. Create the API gateway and Lambdas using SAM. We're going to send some data using Locust, which is a Python load testing tool. Query the ledger and check the logs. So let's see how that goes. So firstly, hopefully you can see a console now. Gesticulate wildly, Dan, if you can't. So we're going to deploy to CloudFormation the ledger itself. Now, for those of you not that familiar with the command line for CloudFormation, for a long time I hadn't found this command, this deploy command. It's quite nice. It creates a change set for you and then executes it. So it's a bit nicer than doing CloudFormation, create change set, and then CloudFormation, execute change set, as long as you don't want to preview the change set first. But what we are deploying here is this template. If you're familiar with CloudFormation, this should look fairly standard. If you're not, it's going to look like gobbledygook. But we've got a ledger resource, deletion protection. Normally this would be on, but because this is a demo and I want to tear this down at the end of the demo, I've got it turned to false. But normally you wouldn't want people to delete your immutable ledger. And we've got this new standard permissions mode. I'm calling my ledger API ledger, and we're going to reference that in various things. It's part of the ARN for the ledger. We've got a Kinesis stream that's going to receive all the data. We have a role that allows QLDB to write to that stream. And we have a sort of QLDB stream resource that effectively ties together the ledger and the stream. And then you saw that we had a topic in that diagram. So we got that topic. We've also got a queue that is subscribed to that topic. And then this is just binding those two together and giving the topic permission to write to the queue. So fairly standard stuff. And that's being created. So we should now have a ledger. And this is where I try and find the right thing. So we've got a stack there. And if I refresh this, I should now have a ledger. Down here, I have 0 tables, so it's not very useful yet. I'm going to say query ledger. And I am going to say, and I'm going to copy this because I don't want to get it wrong. It's in the README. Get these two commands. Because if I do something silly and call the table API events rather than API event, it's all going to go horribly wrong. So first I'm going to create the table. I get back a unique table identifier. This is what you would use in an ARN if you were doing roles where you limited access to an individual table. And then I'm going to create an index on the ID attribute of that. And you can see down here, I've got an index on the ID field. Great. Now I'm going to create Lambda functions and the API gateway. Now, if you've used SAM before, normally you would do a SAM build. It creates the sort of packages up the Lambda functions. Because I've already done that before, and to save time, I'm just going to deploy it. So it's just going to do the CloudFormation deployment of those Lambda functions. And what we're doing here, I will quickly show you the SAM template and the actual Lambda function itself. So if you've not used SAM before, but you have used CloudFormation, the main difference between the two is this transform. Think of it as a macro. It's very similar to the custom macros you can build yourself in CloudFormation. And it allows you to have magical things like this AWS serverless function resource. And what happens with this is it takes this resource and it creates multiple resources from it, one of which is an AWS Lambda function, but it also creates an IAM role. And in this case, just by having this event declared here, it will create an entire API gateway and associate that with this Lambda function. Now, there's more than that. You know, if you want more complex setups, you can do that, but there's quite a lot of power to what this transform can do. Now here I'm directly putting in line the permissions I want for the Lambda function. So I've got permission to write to the topic, and this uses a pre-built policy that you can reuse. But for this, for QLDB, there isn't a pre-built policy. So I've just put permissions in line. So this first section essentially allows me to connect and send commands to the ledger, and the ARN is the ledger ARN. And then we've got table level permissions, and these are those new fine-grained permissions to allow us to do select, insert, and update only. And I'm actually saying grant permission to all tables, but I could have the table ID in here. But because that's different every time I stand up the ledger when I test this demo, I didn't want to mess up by putting in the ID and forgetting to change it. So by now, yep, we have an API gateway. So I'm going to copy that. And I'm going to run locust. So locust is a Python load testing tool. This is just going to run a little web server that I can use to kick the test off from. I'm not going to start the test quite yet. I'm going to show you a few more behind the scenes. So let's have a look at that locust file. This is the event we're going to be sending, and we're just going to randomize some of this data. We're going to run a number of concurrent users, and it's going to use a random ID between 0 and 99. So that means we should in total get 100 unique IDs. We've got a timestamp that's just going to increment to the current date. So if we send an update, we should see the timestamp increasing. And we got another value that just randomly changes. And that's all we're going to do in the test. And we got some nested data structures so we can query into those and see how those look as well. Now, as for the actual API code, this is the entry point, the handler function for the Lambda function. We do some setup work here, get some environment variables, create a Boto3 session to allow us to use the SDK for AWS, create a client for SNS, and then there's a separate package for the Python QLDB driver, and that takes a session and the name of the ledger. In the handler itself, there's not really much logic. Really, the magic happens in this one method here. So we're calling execute Lambda and everything, and this Lambda is Lambda in the Python sense, not Lambda in the AWS sense. Everything that happens within this Lambda is going to be a single transaction in QLDB. So it's calling this upsert event. We're also passing in this function to do the SNS sender, so that that's hidden away from this method here. And the actual work in there is in this operations file. So this upsert, and this is very much what we saw in the slide. We've got a select, an update, and an insert. So first we use the simple iron library to convert what's a string version of the JSON event into an iron document. We check that it's got an ID because otherwise we can't index it. And then we do a query. And if we get a record back, we're going to do an update and log that we did an update. Otherwise, we're going to do an insert. And additionally, we're going to call that sender method, which will send to SNS. And we're going to log that we sent to SNS. So we should be able to see that in the logs when we run this. Okay, so that's the explanation portion. Let's actually see this doing something. And of course, there we go. So we're just going to start with one at a time, and we're just going to verify that we're not getting failures. So that's good. We got a few requests coming in. So now we're going to query the ledger. Okay, we've just got 6 rows so far. If we look at the functions, you can see we've got our 2 different functions. And if we look in CloudWatch, we've got log streams for both of them. We got a single copy of the API. And we can see here we've got that insert sent to SNS, insert sent to SNS. And here we've got our first update down there. We reused 6 already. Okay, that's all well and good. Now I'm going to ramp this up. And I'm not going to be subtle. When was I ever subtle? And we're going to go straight to 100 users. So what we see here is our response time and our request per second. So we were, we get a bit of a sort of spike at the start because the Lambda functions are cold. So once those are initialized, then we get response times around 200 to 300 milliseconds. Another spike as I increase the number of users as it spins up more copies of the Lambda function. Then it goes right back down to that same sort of level of response time, but we're now doing about 34 requests per second. So that's fairly reasonable throughput. And if we look in our ledger and run this select again, we're actually overloading that slightly. So we'll just run that again, and we should, because I'm not doing any sort of index query, I'm scanning the whole table, so that's always a possibility, but you can see I've got a count of 100. So I'm just going to pick one of these at random, ID equals 22. Now this is an index field on the table, so we should be pretty confident that we're going to get a reasonably fast response, and we've got that coming back. Now I'm going to try and remember QL committed. Hopefully I've spelled that right. Yep. Oh, I got another concurrency. I'm going to slightly trim this down because I am kind of hammering it. I don't know that the QL committed is indexed in the same way. I put that in because I saw it in Dan's slides, but I didn't actually practice that. So there we go. Oh, I must have misspelled that. Because that was not part of my demo, I am going to move on because that's embarrassing. So what I really am interested in, though, is not so much that as the history view. I'm going to say h.data. Okay. And so I now have 41 versions of this particular record where the ID is 22 that have now been added to the ledger. Now, here's our data. So this is why I did h.data.id, because it's a nested object in here, and then I'm looking at the ID field here. Now, if I scroll here, you can see those block and hash, that's that cryptographic information. And in the metadata, this is a document ID for this. And then I have a version, and 1, 2, 3, 4, 5. Now, while this worked for me here, if I'd have still had that running 100 users, this would have probably given me a concurrency error as well, because this is not indexed on the history function. It is indexed on the table, but not on the history function. So if I want to efficiently query the history, really I want to use this ID. Now, obviously, I'm not going to cheat and just copy, well, I'm not going to cheat and copy this from the history, because if you can query the history, then you didn't need the document ID. So there is a way to get the document ID. Select, say, EID from API event by EID where. And this will give us the unique document identifier, which is exactly what we saw in the history. And then instead of querying by data.id, I'm going to query by metadata.id with that string. And that is an indexed query, and therefore much less likely to have any concurrency issues and be more performant. Now that's all well and good, but one of the nice things about Particle is being able to do things like this. So that's a rather nicer presentation of the data as it's coming back. We've just got our data, our version, and then the fields out of the data coming back. And so we can see how the timestamp's increasing over time, and the changing value is, just some random number between 0 and 1,000. We are also, you could also take this array here and just pick out the first item, or filter where item ID is 1 or some other value, or the description was a particular value. So there's a lot of things you can do of sort of projecting into this document that you can do with the particle syntax. Now, there's a couple more things I want to show you. Now, we said we've got a queue here, and this is interesting. So if you remember, when I said I was going to send to SNS whenever I inserted into the ledger. And we queried the ledger and there's 100 rows. And yet there's 119 messages available in the ledger. That's not quite what we expected or hoped for, and I'll explain that as a second when I go back to the slides. What I also do want to show you, well, a couple of things. Just, we've got a bunch of streams here because it's spun up a bunch more Lambda functions to handle the load. And we've also got what the stream is doing. If I look at what the stream's doing, you can see it's receiving chunks of events. It's only looking at revision detail records in the Kinesis stream, and those are ones that contain changes to data. There's a lot more information about the ledger that comes in the stream, so we're selectively picking that. I'm not going to look at the Python code for this in the presentation, but you can look at how that works if you go to the GitHub repo. But you can see what it's doing here is it's printing out the document identifier, the version it's received, and the iron in this format. You can see it's not quite JSON. It's got less quoting than JSON, which is always a nice thing. Okay, so let's talk about what happened here. So what could possibly go wrong? Well, we got more messages than we expected. So this is our original architecture where we've got SNS being called by the Lambda function and then going off to SQS. But there is a chance of duplicate records going to SNS. And why is that happening? Well, if we look at what the code did, here we're doing an SNS send. And remember, everything in this method is occurring within a transaction. Well, what if our random load test tried to do multiple events or multiple inserts for the same ID at the same time in parallel? So there's a very strong chance of that in the way we randomly picked between 0 and 99, and I did a spike of 100 users. So what's going to happen is they both get to this point potentially, they both successfully send to SNS, and then they both try and commit. Well, only one of them is going to be allowed to succeed on that. So the other one is going to have the transaction rolled back and automatically retried. By default, the QLDB sort of library for, at least for Python, will retry 4 times with an exponential backoff to retry the transaction. So what would have happened is it would have sent the message of the insert, rolled back, come back again after the other one had done the insert, and then it would have been an update. So we'd still just have the 100 records in QLDB, but we have more than 100 notifications. Now, it may be your application can tolerate that. You may be using FIFO queues where you want ordering to be very important, and perhaps you're using content-based deduplication, and depending if those 2 events coming in are actually identical, it may get deduplicated. But the alternative is to take a pattern like this, where you're consuming from Kinesis, and that's where you're doing your notification. Now, in this example, to do it just for inserts is very straightforward. You just say version is 0 on the data that you received. That's equivalent to an insert, and you send your notification. If you want to do something more complicated where you want to look at your current version of the data and compare it to the previous version of the data, the stream's just going to contain, this is what version 6 currently is. If you want to compare it to version 5, you're going to want to go and query back in the history and pluck out version 5 and do a comparison between the two. So there's potentially more work if you need to do that. The one thing I would say is there is a chance of out of order records in this use case because the Kinesis stream does not guarantee ordering. Now, like a lot of things, chances are 99.99% of the time it will be ordered, but that may be a reason for looking at the other approach. But this way you will only get data that has been committed to the ledger, so there's no risk of these sort of phantom events that we got in the other design. So with that, that kind of concludes my demo. So I know we had a few questions already answered in the Q&A, but feel free to ask any others that you have. Hopefully I didn't blind you completely with that demo. Okay, well, I'm going to leave the question that's in there to one of the Amazon folks.
So for the question is, for persistence, how does QLDB compare with relational, with history temporal table, which can be controlled by access role? So the key differentiator for QLDB is that there's no one super user in the database that has the access rights to tamper with your transaction history. Typically in a relational database, you've got audit tables, and you have the ability, there's always somebody with the ability to tamper with the data, whether it's your source data or whether it's the audit history. With QLDB, you just can't do that. And then the cryptography allows you to mathematically prove that it has not been tampered with. And so with other databases, it really is difficult to truly say that your data has not been tampered with, that it is what you expect it to be. Whereas in QLDB, the way the journal works and the way the cryptography works, and then of course the fact that we don't surface functionality from modifying the journal, all those things contribute to adding integrity to your transaction history, to making sure that your data truly is immutable and provably so. How do you handle writing mistakes written to QLDB? Just interested in your thoughts on this. Well, immutable means immutable. So whatever you put in the database is there for the life of the database. So there's good news and bad news to that. If you put a mistake in the database, well, then that mistake will be there forever. But the great thing is, you use QLDB to provide transparency into what you're doing. And so you'll have a record of the mistake and a record of the correction. That'll be in the historical record for all time. So the way you'd correct the mistake is to append a new revision of that error record to the journal. And like I said, you would have a record of the mistake and the correction. So that could be good or bad depending on your outlook. I think it's good because it provides great transparency into what you're doing, which is why you're using QLDB in the first place. Is there an equivalent offering by AWS for a decentralized ledger that still uses some of the cryptographic mechanism of QLDB? Well, we offer Amazon Managed Blockchain, which is a true blockchain. So that is a decentralized ledger with a consensus mechanism and an ordering service and everything that you would see in a typical blockchain. Amazon Managed Blockchain is a managed Hyperledger Fabric or Ethereum service. So you have a choice of which framework you're going to use. So if you're looking for an actual decentralized ledger, then you're probably looking at a traditional blockchain use case, and we do have a managed service for that. We also have a lot of customers that run blockchains on EC2. So they don't want to use a managed service. They want a bit more control over their setup. And so we do have a lot of blockchain running on our virtual machines. But for managed services, Amazon Managed Blockchain would be what you're looking for. If you delete a record, can you restore it? If so, does it just add to that history? So as we saw in the example, you don't actually delete a record. You're essentially creating a tombstone. You can't restore it in the sense that you can't revive that record with the same document ID. You essentially have to reinsert a new record. And so while the transaction history will still be there and accessible in the history, your new document will have a different document ID. So it'll have a different identity. So there's no way to restore a so-called deleted document. Next question from Bryce, kind of related to the record of mistakes. Is there any future plans for allowing journal forks? Not at this time, but if you need some kind of functionality like that, please reach out to us, let us know. Guys like Eric, product managers for QLDB, will be really interested to hear your use case and your requirements to see what that might look like in the future. Michael asks, is there a way to link those, or is that not something that is really required for an audit? What do you mean by link those?
I think he's following up to his deletion question.
Oh, I see. So what you could do is you could store a field that has the document ID of the old field. The database doesn't do that for you, but if you wanted to do that, you absolutely could. You could store a link field if you wanted to, and you could even use that to join, do an inner join over to the history function. So that could be a way of navigating from your new record to the old record that it replaces.
Yeah, so in my example, if I'd have deleted one of those records using the sort of ID field and then just ran the data again to send more events, it would just do an insert because the select wouldn't find a match and it would just create a new document ID. But what Dan's saying is you could then take those document IDs and perhaps put in a value to say this is actually a continuation of this previous document. Okay.
All right, and we have a question, follow up to the fourth question. Can you run hierarchical queries on QLDB? You can certainly query into the hierarchical data structure of your document. So if you have elements that are nested several structures down, you can dig into those with a really easy to use syntax using particle. There's no functions to invoke. There's no extensions to invoke. That's a really simple syntax. I hope I'm answering your question on that.
Okay. Yeah, so that's kind of what I was doing here. But you can also do something like I'm going to mess this up. Say, yeah, I've messed that up, haven't I? Oh, yeah, that's just this. Yeah, so now I've gone into the details, but I could actually say, I think I can do this. Yeah, that kind of thing. And you could then filter and just pick out, where item ID was 1 or something like that. Okay, well, I think that was all the questions we had. So here are those links I promised. So that's the link to the GitHub presentation and Dan and my LinkedIn links. If you're interested in joining the Columbus AWS Meetup, if you're not already a member, that's the link to the meetup where future AWS meetups will be announced. And there's the Leading Edge website. There should be a short survey at the end of this presentation, but I have no idea how that works. So I think what it will do is when you exit the webinar, it will open the survey in your browser. But I may be wrong. We're fairly new at using the Zoom webinar platform, but I think that's how it will work. And we'll just ask you, there's literally 4 questions about, your interest in QLDB, and also if you're a member of the meetup, whether there's particular topics you're interested in. So thank you to everyone for attending, and hope you have a good evening.